Alright, today we're going to have a look at the introduction to our first extension 2 topic, which is complex numbers. So, from kindergarten, we have learnt about natural numbers, which is like 1 and 2 and 3. And over the years, we added things to this like 0 and negative numbers, which we call the integers. We then later, had fractions introduced, which we called rational numbers. And later on, as you did Pythagoras' theorem in year 8, you learnt about irrational numbers, like the square root of 2. We're going to learn today that there's actually another set of numbers. There's one more after today's one, which you'll learn in university. But today we're going to learn about complex numbers. So, imaginaries, i's, and complex numbers are numbers that have what we call real numbers combined with complex numbers. Now, just like real numbers, our imaginary numbers can also be rational or irrational. So all numbers, whether they're real or imaginary, are what we call complex numbers. All numbers consist of a real component and an imaginary component. But most of the numbers that you've worked with before, in fact probably all of them, have had an imaginary component of 0. We're going to introduce what we mean by an imaginary component, and together they form a complex number. So the most important thing that you're going to look in this whole topic is this cool number called I. So I was defined as to be the square root of -1. We know that normally we did the square root of -1, we would get math error on our calculator. And think, right, to square root a number means that we want two numbers that multiply by itself to get that number. And it doesn't make sense for the square root of a number to be negative or to take the square root of a number, because the definition of square rooting is thinking about the same number that multiplies by itself to get our result. And we know that two negatives make a positive, so it's impossible for a negative number times by itself to be negative, which is why we can't square root -1 or -5. So back in the 1600s, mathematicians, decided that they've run out of numbers. They'd like to have some more numbers, and they wanted to make some up. And specifically, they wanted to look at the square root of -1. And they defined it to be I. And funnily enough, I does stand for imaginary. They imagined this number to exist. It's pretty cool that they just came up with something. They imagined it to be true. They defined it to be true. And today in 2025, it is an extremely, extremely useful, although made up, what we thought at the time, property that we use in engineering mathematics. So I is defined to be the square root of -1. Specifically, I squared is equal to -1. That's the better definition. Okay. So, for example, we know that we can find the square root of 4. We get 2. But the square root of -4, well, that's the same as the square root of -1 times the square root of 4. And the square root of 4 is 2, and we've defined the square root of -1 to be I. So the answer is 2i. The square root of -3 consists of root 3 times root -1. Now root 3 we know is like 1.7 or something, but if we just left that there, we could say root 3i, because the square root of -1 is I. I squared is -1, and I cubed is I times I times I, which is I squared times I. But we've defined earlier that I squared is -1, so -1 times I is -I. So all of the examples that we've just looked at have been determined to all be purely imaginary, apart from example A. These three examples here are what we call purely imaginary numbers, which means they only consist of an imaginary component. So we call these numbers purely imaginary or just imaginary. Complex number, which is the title of this topic, however, is a number that consists of both an imaginary number, an imaginary component, and a real component. So as we can see here, a complex number, z, we usually use z for complex numbers, is a, which is my real part, plus ib, which is my imaginary part. Now technically all numbers, as I said earlier in the video, are complex numbers. All numbers have an imaginary component and a real component. However, most of the time the imaginary component is 0, or what we just saw, the real component is 0. Now you're going to learn, and we're going to learn soon in extension 1, that complex numbers are vectors. Now a vector cannot be ordered, which means that the imaginary number 1 plus I doesn't necessarily lie before 3 plus 2i. It doesn't make sense to order them because they're not a normal number. They're what we call a vector, which is more representing a coordinate on the Cartesian plane. This is actually the coordinate 1i on the Cartesian plane, and this is 3, 2i on the Cartesian plane, and it doesn't really make sense to order those. Now, we can only add real components with real components and imaginary components with imaginary components. We can never do 3 plus 2 because they're not like terms. They're actually different parts of a vector, which you're going to look at more in extension 1 and then later in this topic. Okay. Oh, that's a mistake there. Okay. Okay, so a few things. The addition and subtraction of a complex number. To add a complex number, we just add the real parts and we add the imaginary parts. To multiply two complex numbers, we're going to look at that. We multiply them together and expand it out like we would expand a binomial expansion. The conjugate of a complex number, if z is equal to x plus iy, then the conjugate of z is z bar equals x minus iy. So that all that changes there is the plus becomes a minus. And lastly, we're going to look at this in a second, the division of complex numbers. To divide complex numbers, for example, z1 divides z2, we multiply the numerator and the denominator by the conjugate of z2. This process is known as realizing the denominator, and it's a play on rationalizing the denominator, which you would have seen in Year 10 and in advanced maths. So our second example for today, we're going to find z1 plus z2. So z1 is equal to 2 plus 3i, and z2 is minus 1 plus 4i. Okay, part A, z1 plus z2 is 2 plus 3i plus minus 1 plus 4i. 2 plus minus 1, we're adding our real components, is 1, and 3 plus 4 is 7, plus 7i. z1 minus z2, part 2, we've got 2 plus 3i minus 1 plus 4i. Let's expand through that negative. 2 plus 3i plus 1 minus 4i. Just quickly add another page there. So 2 plus 1 is 3, and 3 minus 4 is minus 1. So 3 minus I. Part C, let's multiply these complex numbers together. z1 times by z2, 2 plus 3i, and then minus 1 plus 4i. We're just going to expand it out like we normally would with any binomial expansion. So 2 times minus 1 is minus 2. 2 times 4 is 8, so 8i. Minus 3 times minus 1 is minus 3i. And then 3i times 4i, well, 3 times 4 is 12, and I times I is minus 1. So it's actually minus 12. So our answer is going to be minus 2 minus 12, which is minus 15, and then 8i minus 3i, which is plus 5i. Okay. Part D, we're going z2 times z2 bar. Now, z2 bar is the conjugate of z2. So we've got minus 1 plus 4i times by z2 bar, which is minus 1 minus 4i. So the conjugate, we replace the minus with a plus, or vice versa. We just expand that. 1 plus 4i minus 4i. And then from 4 times minus 4 is negative 16. And then I times I is minus 1, so it's positive 16. So our answer is 4i minus 4i is 0. And 1 plus 16 is 17. So we would say that z2 times z2 bar is purely real, which means it only consists of a real component. Its imaginary component is 0. Look at part E, z1 all squared, so 2 plus 3i squared. So 2 plus 3i squared, we've got 4 plus, we multiply the middle 2, 2 times 3i is 6i, double it, we get 12i. Then if we square the last term, 3i all squared, well, 3 squared is 9, and I squared is minus 1. So this is minus 9. So we've got 4 minus 9 is minus 5, and then plus 12i. Okay, last one, part F. Z1 divides Z2. 2 plus 3i divided by Z2, which is minus 1 plus 4i. We have to simplify this fraction here. Now, just like in rationalizing the denominator in advanced maths and year 10 maths, we don't like in rationalizing the denominator, for some reason we don't like square roots on the bottom. It does make sense. It makes it easier to add the fractions together. And same idea with complex numbers. We don't like imaginary components on the bottom. So we're actually going to multiply the top and bottom by the conjugate of minus 1 plus 4i, which is minus 1 minus 4i. So on the top, we've got this, 2 plus 3i, multiplied by minus 1 minus 4i. And on the bottom, we've got minus 1 plus 4i, minus 1 minus 4i. So if we expand the top, 2 times minus 1 is minus 2, minus 8i, minus 3i, and then what I think we've seen earlier, potentially, 3i times minus 4i, 3 times minus 4 is minus 12, and I times I is minus 1, so it's plus 12. Over, if we did that expansion, you might realize that this is actually a difference of 2 squares. The same thing, except that's a plus and a minus. And a difference of 2 squares tells us to do x squared minus y squared. So minus 1 squared is 1, and 4i squared is minus 16. No, I'm sorry, 4i squared is positive 16. So plus 16. And I'm sorry, I made another mistake here. X squared minus y squared, that's y. And then 4i squared is minus 16, but then those two negatives in the middle make a plus. Okay, minus 2 plus 12 is 10. Minus 8 minus 3 is minus 11. I over 17, and that's the answer there. And that's what we call realizing the denominator. Realize means we've made it real. If we wanted to do this expansion here properly, I might, because I messed up earlier. We've got 1 plus 4i minus 4i, and then we've got 4i times by minus 4i. 4 times 4 is 16, so 4 times minus 4 is minus 16. And then I times I is negative 1. So we've got minus 16 times minus 1 is 17, and then plus our 1, minus 16 times minus 1, I'm shocking today, is 16, and then plus 1, we get 17. Okay. Another nice property of complex numbers is something quite exciting, that we can solve previously unsolvable equations. So when factorizing and solving equations, we often pause whenever we have a discriminant less than 0, since we can't normally square root a negative number. But now we can. So let's solve these two. Z squared equals minus 4. So Z equals still plus or minus the square root of minus 4. But we've decided earlier that the square root of minus 4 is 2i. Okay. Example 2. In the past, it would not have been, or part 2, it wouldn't have been possible to solve this because if we start using the quadratic formula, so 2 squared minus 4 times 17 is negative 64 over 2a, which is 2. And now the square root of negative 64, well, the square root of 64 is 8, so it's plus or minus 8i all over 2. So that gives us minus 1 plus or minus 4i. Now we can also use this to factorize previously things that were unfactorizable. So if we actually use the quadratic formula to solve this, a very good method to quickly factorize something if you can't think of its factors is to quickly chuck it in the quadratic formula. So we've got z equals minus 2 plus or minus 2 squared minus 4 times 26 is negative 100, I think, minus 100 over 2. So minus 2 plus or minus 10i over 2 is minus 1 plus or minus 5i, and that's equal to z. But that actually means if we were to subtract everything to the other side, z minus 1, if we do our plus 5i first, it would minus over to be minus 5i equals 0. We plus. So I've actually gone and minused all of these things to the other side. And then if we did it again, z plus 1, if we got our z equals minus 1 minus 5i, if we plus it to the other side, we've got plus 5i equals 0, which by our null factor theorem means that question there can actually be factorized to give this nice thing here, which in the past would not have been possible to do. And that's done there. Okay. Now questions can ask us to factorize things over the set of real numbers, but also the set of complex numbers. So if you did the holiday homework that I set for you guys to do in the holidays, you'll know that this factorizes to be z plus 4, z squared minus 4z plus 16. And if you did the quadratic formula to attempt to factorize the thing in the middle, you're going to get a negative discriminant. So over the set of real numbers, we're done. But if the question said factorize over the set of complex numbers, it's a bit more involved because we can actually use our knowledge of imaginary numbers. So if we quickly use the quadratic formula, we can say z is equal to 4 plus or minus. Now 4 squared minus 4 times 16 is negative 48 all over 2a, so 2. So that gives us z is equal to 2 plus or minus, the square root of 48 is 2 root 3, so the square root of negative 48 is 2 root 3i. And then we can say, okay, well that was z equals 2 plus 2 root 3i, or z equals 2 minus 2 root 3i, which means we could say z minus 2 root 3i is equal to 0, or z minus 2 plus 2 root 3i is equal to 0, which means this z squared minus 4z plus 16 can be written as z minus 2 root 3i, z minus 2 plus 2 root 3i, and of course we still had our original z plus 4. So what we've just done is factorized that seemingly simple equation into something that involves a real component and then also imaginary components. Now here that we can see each expression individually in each bracket is linear, which means the power on our z is 1. So this is why these questions, instead of saying factorize, they might say express it as a product of its linear factors. So if the question didn't have any of this or any of this, it might say express as a product of its linear factors, and it means factorize over the set of complex numbers. So hence solve z equals the cube root of 64. Well, from here we can see if we made this expression, if I copy it, copy this, not cut, copy. If I make it equal to 0, because we figured out earlier that this factorizes to give that, so we can say, okay, well that has to be 0. That means z equals minus 4, or we figured out earlier that z was 2 plus or minus 2 root 3 I. Those are the answers to that equation. Alright, thanks for watching.